Hello, I hope you're doing well. In this video, I want to take you along the journey that I went on to develop the latest and hopefully greatest version of Jugglebot's hand. Now, to understand what this design is all about, we need to first go back and have a look at the problems that I was having with the old design. Now, if you've seen my last video on Jugglebot's hand, you may remember that I was having issues with the hand sticking on the guide rods as it was sliding up. And this is a deal breaker for Jugglebot, basically, because the hand needs to travel very smoothly to receive and throw the ball in order for the ball to actually stay held. I don't have any fingers or anything on Jugglebot, so there's nothing that will actually hold the ball in place once it's on the hand. It just has to stay within its little cup part the whole time through. And the only way that that's going to reliably happen is if the ball does not move relative to the hand once it's been caught, and if it doesn't jiggle around at all. The only way that's going to happen is if the hand travels really smoothly along its entire path. So sticking and jittering around, not allowable. Now, I did mention in that old video that adding constant force springs to the hand to pull the little slider things back in should help the problem quite a lot. And I ended up doing that for my next design, which I have here. And we can see on the bottom here, there are constant force springs that pull the sliders back in again. And this design works really well. It slides quite nicely on the rods, but it still gets stuck occasionally. And as I said before, sticking is not okay. There is one other thing that I changed with this design as well, which is that I cut out a large part of the section that grips on the upwards guide rods. And the reason why I've done that is because it allows the little sliders to have a bit more wiggle room, and the idea there was that it would stop them from binding and catching as often. And it does a pretty good job. This slides relatively freely and only really gets caught when I push it at weird oblique angles. So this design does do a pretty good job of not sticking, but as I said before, it's not perfect, and every now and then it will stick, and I really want to try to remove this as a source of problems in the future. So sticking is not allowed. The second problem is one that I haven't actually had yet, but I've been anticipating it for quite some time. And that is that if the ball comes in and Jugglebot is slightly off in its timing, then the ball is going to hit what is essentially a rigid plate and jiggle around and move and do things that I don't want it to do. So for the same sort of reason as the hand sticking, the hand being out of sync and too rigid is a problem. Now, I could tackle this from the out of sync perspective, where I try to ensure that the motors are perfectly in sync all the time, but with reality being what it is, I don't think it's realistic to expect the motors to be to the microsecond correct every single time. So for a long time, I've been trying to think of ways to incorporate a spring or a damper into this system to absorb any excess energy from the ball before it leads to the ball jittering around. But I haven't been able to figure that out yet. Thankfully, there is a solution to both of these problems, and that is to use a compliant mechanism. Now, compliant mechanisms are a relatively new field of engineering, and they involve designing systems that bend and flex to achieve a desired motion, rather than relying on rigid links connected with hinges and that sort of thing. By making the hand out of compliant parts, the ball will be able to dissipate some of its excess energy into the printed hand part, rather than jiggling and bouncing around. Secondly, because the hand will be compliant, it will be able to bend and move around, which means that if the cables that pull the hand up are slightly out of sync, then it shouldn't get stuck. And this was a big problem with previous designs, where if I tried to just pull it up on one side, I can't do it. It gets stuck. So if these cables are out of sync by very much at all, then the whole thing just gets jammed up and it's not going to go anywhere. To give a general overview of this new design, I decided to bite the bullet and get linear bearings to go inside here, and these ride along the sort of vertical rods of the hand. And to be honest, just using linear bearings probably could have fixed the sticking problem from before, but I think the compliant mechanism still helps that problem by allowing a little bit of offset, and so I think the linear bearings plus the compliant mechanism will completely fix the sticking problem. There are also constant force springs in the back here, and these help to pull the carriers back in, and will help pull the hand back down faster than gravity otherwise would. The real meat and potatoes of this design, though, is the compliant nature of it. And you can see here that it's actually very, very, very compliant. So I can hold that fully horizontally, and this part, it's sort of hard to capture on camera, but this can bend quite a lot and move around quite a lot. And it's very nice to play around with. It's got a really nice feel to it. What I want to walk you through now is how I actually went through the design process to arrive at this exact layout. And it's not super trivial, but it's actually not that hard if you have access to a good CAD software like SolidWorks. The first step to designing any compliant mechanism is to first figure out what motions you want your mechanism to achieve. In my case, I want the cup part of the hand to be able to sink lower than the sliders, which are, for all intents and purposes, rigidly fixed in place because they're being held by the cables that wrap around down to the ground. For this to happen, the slider rods need to bend upwards, which means that both the cup and the sliders need to flex. So I need two types of compliant mechanism here. Because I think it's more interesting, let's have a look at the cup part first. Now, this part has two design requirements. The first is that it needs a ball sort of shaped part to actually catch the ball. And secondly, as we've just figured out, it needs to be able to allow the rods that the sliders run along to tilt upwards. The first part is pretty straightforward. I just need to have a little spherical cutout of whatever I end up making and job done. That can receive the ball. The second part though, of allowing the rods to tilt upwards, is a little less straightforward. I'm not going to go into full details right now of how compliant mechanism design works, but what I will suggest is that if you're interested in this, and it's a very interesting topic, I suggest checking out the lecture series delivered by Professor John Hopkins on YouTube. This is a super interesting lecture series, and I have learned a tremendous amount from it, even though I'm only up to lecture 7 of, I think, 12. It's really good. I strongly recommend it. As for this specific problem of needing the rods to tilt upwards, it should be relatively intuitive that if you have a thin sheet, and if you fix one end and push the other end, then that end being pushed will tilt upwards. It will also move upwards, but I don't really care about that motion. I just care about it tilting upwards. So if I can attach my rods to the center of the hand via a thin sheet, then I should get the desired compliance that I want out of my design. There is one problem with this idea though, which is that I don't have very much space in the hand, and the stiffness of the sheet is very closely related to how long that sheet is. So if I was attaching the rods with just a very short sheet, it's not going to be able to bend very far compared to if it were a long sheet, and then it can bend really far. The solution that I found for this was to route that thin sheet around the perimeter of the hand, so that the sheet is actually comparatively quite long, and quite a bit longer than it would have been if I just connected the rods straight to the center with just a little sheet that's like connecting along here, for example. Now, this, for example, like this section of rods is connected all the way around here, and all of that section can flex to allow this whole part to move. So we know from this thought experiment with pushing the card up and down that attaching the rods to the center point with a thin sheet will give us the desired motion that we want of the rods tilting upwards. But a really important part of compliant mechanism design is in making sure that your design does not permit any motions that you don't want, because it's very common when designing a compliant mechanism to have it be allowed to move in ways that you probably don't really want it to move. There is a mathematical way to check the full space of motions that your design permits, and it's very cool. I strongly recommend watching that lecture series from before. But thankfully, we actually don't need to employ any maths or geometry or anything like that if we have access to a good CAD software like SolidWorks. There is one thing that we need to touch on before we get into that though, and that is resonance. You're probably familiar with resonance as being something that you usually want to avoid because it can often lead to large and uncontrollable motions that lead to whatever is resonating being destroyed. This is exactly the case for the singer who sings and destroys the wine glass because it just vibrates so much, it just vibrates more and more, and then it breaks. Now this is absolutely correct, and resonance should usually be avoided, but this misses out on something that's pretty important about resonance, which is that depending on the frequency that you are stimulating an object at, it will resonate in different ways. These ways are called modes or mode shapes, and they're often quite pretty, as you can see here with this square plate. To generate these modes, I'm making a SolidWorks frequency simulation which sweeps through all frequencies and shows the first 5 mode shapes for the given object based on the material and the boundary conditions that I've applied. In the case of this square plate, it's being fixed at all 4 sides, and so only the middle part is allowed to actually move. This relates to compliant mechanism design because the mode shapes that you get as a result of doing a frequency sweep almost always correspond to the ways that your design is happy moving in. And so what you can do is run a frequency sweep see what your mode shapes look like, and that will show you the ways that your object will move. That way you don't need to print it off, you can just prototype from your computer and see exactly what it's going to do. For the current design of the hand, this is what those mode shapes look like. We can see pretty readily that modes 1 and 2 are basically the same, they're just twisted around a little bit, and are more or less the desired motion, except one side is moving with the other two being stationary. So that mode that's pretty fine, like that's motion that we're happy with. Mode 3 is exactly the desired motion with all lobes lifting up, but modes 4 and 5 are not desired at all. I really don't want the hand to be moving in those ways. Thankfully, there will be no force exerting a twisting motion on the hand, so mode 4 won't be an issue at all, and mode 5 shouldn't be a problem since I really can't think of how the actual forces involved would work to deform the hand like that. So, after running a frequency sweep and checking the first 5 modes and confirming that they're either deformations that we want or deformations that aren't a problem, we can be pretty confident that this design will give us the exact output that we want and should be quite rigid in all other directions. Now that the cuff part is done, we need to do the same thing but for the sliders, because if the sliders don't allow the rods to twist, then they're not going to be able to twist at all anyway. My first design for the sliders looked like this and had these mode shapes. After seeing these really weird mode shapes that were created by this design, I went back and changed some parts around to arrive at the current design, which looks like this and has these mode shapes. Note as well that I also added on 2 little tabs to hold the constant force springs, which I didn't have on the original design because I was still just prototyping then. This second design behaves much more nicely, with mode shape 2 being the exact form of deformation that I want. Mode 1 shouldn't happen because there won't really be any forces acting to deform the body like that, and the same thing goes for modes 3, 4, and 5. So I can pretty confidently say that they shouldn't cause too many issues for me. Putting everything together gives this. This design has a really nice sponginess to it, and will hopefully do a really good job of absorbing any of the excess energy that the ball has on its way in to give it a nice smooth catch. If I do need to adjust any of the stiffnesses here, I can just simply adjust the thickness or the length or whatever geometry I need to of that thin sheet so that it is more stiff or less stiff as needed. This design also slides really nicely along these rods, and to be honest, that's probably almost entirely thanks to those linear bearings. But the compliant mechanism part helps as well because it allows the asymmetry between the cables that pull this slider up to be quite a bit more. Like this can raise up way more than the old design could. And even though I'm only pulling one, I can still sort of pull the other ones up as well. It's a much, much more robust design than the one before was. This should slide even more smoothly once I've put this whole component into the rest of the frame that makes the top part of Jugglebot, because this will hold these rods in place so they don't bend around like this, and it will make the whole thing a lot more rigid. The only reason why I'm keeping it separate for now is because I didn't really design this whole mechanism to be like reattached over and over and over again, and the parts that hold these rods are starting to break a little bit, and I'm keeping this separate for now just while I'm prototyping the hand until I get this pretty solid, and then I'll put it all back together again. There are undoubtedly going to be problems with this design at some point in the future, and I'm almost certainly going to have to change it. But for now, I'm super happy with this design. I think it is working a lot better than the previous design was, and I'm very keen to see how well this works once I actually get everything put together properly. That brings us to the end of this video. As always, I hope that you found it interesting, and if you have any thoughts at all, then please let me know in the comments below. I'll see you in the next one. Till then. Very spongy, and I can actually